Hey everybody, we're going to learn a little bit about metals and how we can determine maybe some charges on transition metal elements or oxidation states. We're going to name some of the compounds and maybe even, maybe even look at some structures and some other neat stuff. So let's get started by talking about what coordination compounds are. Okay, coordination compounds are compounds that have, the best way to put it is they look kind of funky, okay, and coordination compounds are compounds that have metals with ions kind of attached to them, but they don't have to be ions. They could be elements or compounds. There's all sorts of weird things that can attach to these metals. And so what happens are the metals usually occupy, and I'm going to break out a thing from VSEPR theory, but the metal usually occupy what we call the central atom, and then around the outside we form, or we put the ligands, the things that attach to the metal. So we may have a metal here, and M is a chemistry abbreviation for any metal. We may have a metal here in the middle, and then here we may have, look, here's an N3. And then here we may have a water, H2O. Okay. Here we may have a chloro group. Okay, and maybe we have two chloro groups. So the metal here is in the middle. This guy is a ligand. This is a ligand, this is a ligand, this is a ligand. This whole thing forms a complex ion that will be charged. And then when that ion is bound or is attracted to an ion of opposite charge, that becomes the coordination compound. So it becomes this huge sort of crazy thing. We're gonna name these complex ions. Okay, and so here are some things that some names that you need to kind of know. That's going to make naming these things a little easier. Monodentate ligands are ligands that attach only in one spot to the metal. Most ligands, or most things that we're used to seeing in chemistry up to this point, will only attach in one place, like this azido group, or this water, or this Cl, or this Cl. It only forms one bond. But there are a couple that are what we call bidentate, like ethylene diamine. This crazy compound, ethylene diamine, and let me erase that here. Ethylene diamine is what we call bidentate because it will attach to the metal in two places. So again, we have the metal ion the metal atom in the middle, and then we have an ethylene diamine, which it attaches through the nitrogen, and then there's a carbon, and then another nitrogen. It'll attach in two places. So it bidentate, 2 bytes. Okay, monodentate, 1 byte. And that's kind of how they got their names. So what we're going to do is we're going to name some of these compounds just so we can figure out what the heck is going on. So let's name these things. And in order to name them, we're going to go back here and use this list. I'm going to flop back and forth. Now, one of the things that I try to tell people when we're naming compounds is try not to change the rules of naming. And I know that it's probably been a while since we've named some of these compounds, but what I'm going to do is I'm going to cut the compound in half, and I'm going to name the two halves. Okay, I have this half here, which is the negative side. That's the anion. And then I have this side here, which is the cation, which just happens to be a complex ion. Okay, it's named a complex ion because there's a metal with other things bound to it. Okay? So just kind of like how we would name NaCl, this is chloride and this is sodium, so it becomes sodium chloride. That's what we're going to do here. We know this, that's chloride. The only thing is we don't know what this half is. We don't know what the sodium half is. Okay, so that's where these special rules come into play. And so I like to kind of name them backwards. Okay, there's a little bit of a rule going on here, but we'll go from there. Okay, that we have to name the ligands, these guys, in what we call in alphabetical order. In what we call, like, you guys don't know what alphabetical order is. Okay, so let me get this cleaned up a little so that we can do this. So we're going to name the ligands first. So no matter what, we're going to go backwards when we do this. So if we're trying to come up with the name of the complex ion, we're going to start with the ligands and work our way back to the metal. Okay, and the same is true if we have a name. We're going to start at the metal, the end of it, and work our way back. You'll see as I have more and more sample problems here. But okay, so Cl is chlorine. I'm going to go back. So this is this. So it's chloro, and the other one is aqua. Okay, so now when we have coordination compounds, we want to name them alphabetically. And so here's what we're going to do. We're going to name this tetra. Tetra means 4. Tetra aquo. Okay, I guess if you wrote aqua there, because that's what it says on the sheet, that's fine. Tetra aquo. And then, what do we need to do? Let's see. And then this is dichloro. And now we go backwards even more. Okay, and that's chromium. Now, one of the things we have to do is know the charge on chromium. Okay, so this is where it gets to be all kind of crazy. What's the charge on chloride? This guy. Okay, well, that's a minus charge. Chloride is a minus charge. So that means the charge on this complex ion has to be 1+. So CrH2O 4 Cl2, all of this guy has a 1+ charge. So now we have to figure out what the charge on chromium is. So chlorine is a 1-, and there's 2 of them. Water is a 0, and so this plus this plus this all have to add up to 1+. So chlorine, and I'm going to write the total down here, is 2-. So that means chromium has to be a 3+, because water doesn't add to it. So to do this, we do just like we did earlier. We put this in parentheses, like we did when we named kind of binary compounds using transition metals. So it's tetraaquodichlorochromium 3. So that's this ion. The only thing we have left is that part, and so we're going to name that chloride. Okay? Now, here we have a complex ion, and that complex ion is the last half of this guy. Okay? So split it in half mentally, and so what is that guy? Well, that's potassium. And potassium isn't a transition metal, so we don't have to put a thing in parentheses. But now we have to name this complex ion. And notice complex ions can be either the positive, the cation, or the anion half of a molecule. So, let's see here. Name it backwards. tetra cyano. Okay, and this is where it's slightly different, is that we don't name the metal. We put an 8 at the end of it. Nickel 8. Okay, like we would change the name of chloride to indicate that it's an anion, the negative half. Okay, we change the ending of the metal, of the complex ion, to indicate that it's the negative half. So it's tetracyanonickelate. But just like here, we need the charge of the transition metal. Okay, well, in order to do that, what's the charge on potassium? Potassium is 1 plus. How many potassiums are there? There's 4. So this is a total of 4 plus. So that means that this complex ion has to have a charge of 4 minus. So this is NiCN4. And we put the brackets there to indicate that it is a complex ion. And then this is 4 minus. So what is cyano? I'm going to come back here. I want to look at cyano. Cyano is a 1 minus charge. So each of these is 1 minus. Okay, and there are 4 of them, so this has a total charge of 4 minus. So that means nickel has no charge here. Nickelate 0. So that is how we determine the charge there. So the name of this guy is potassium tetracyanonickelate 0. Okay, so I'm going to make sure that there are plenty of sample problems to go over and that there's some worksheets and things like that. Okay, so have a great day and see you soon.